All right, so we're back with part two of the Flexure formula, and before we were just studying the deformation of a structural member subject to pure bending, and we found that the normal strain that bending induces at some location is linear across the section. It's a function of y being linear, and rho is constant. And and what's more is that at a distance y away, we have a strain, a normal strain, and at the furthest distance away, we're going to have the maximum strain. So if we take a closer look at here, let's say this side or that deformation, that deformed shape here, we have this shape takes hold, if you will, right here, where the top is in compression. So the top compresses, it compresses, and the bottom of the section elongates. This is elongation. I don't know what happened. Let me undo that. Okay. It elongates here. And this deformation, these vertical lines still remain, they just rotate. And what that means, because of our strain being linear also, is that if I draw another vertical line here, what it says is that here, beyond my neutral axis, right here, bam, like this is my neutral axis, my NA, right here. Here's my neutral axis. I have at some location above, so here I will say here, this is my plus y direction, my y, positive y upwards, and here at some location I have above here, I have compressive strain, which I will say in red. I have a magnitude of compressive strain here, and then at the bottom of this, I have tension strain right here. And so these are actually numerical values of strain right here, these distances, and this side here would indicate negative strain, and this side to the left would be positive strain. So strain values going this way would be positive strain. Okay, and this is my strain profile. This is what's called a strain profile of the cross section right here. And here I would say at some location y, this is my strain value, that epsilon right here, this minus y over rho, this is a negative strain. And then here at the distance furthest from the neutral axis, this distance c, this is my maximum strain. And because my epsilon max in this case, and the way that we've set this up, is on the compression side, this is a negative, maximum shear strain or maximum normal strain. And by similar triangles, I can say that, hey, this epsilon max minus epsilon max over c is equal to epsilon over y. And this normal strain at any location y can be epsilon is equal to negative y over c times epsilon max. So this right here is this relationship for normal strain at any location with respect to the maximum strain. This maximum normal strain is this value. So this epsilon max represents, this symbol here just represents a number, some value here, okay? Some value there, right there. And so this epsilon here is, it has this variation. And if I apply Hooke's law, now I include Hooke's law. Arr, Hooke's law. I always think of a pirate. I don't know why, right? But here, probably because of Captain Hook. Ha ha ha. Apply Hooke's law, and then that means, which is sigma is equal to E times epsilon, right? Hooke's law for normal stress. And here, I would get that this epsilon is equal to sigma divided by E, bam, like this, and which is equal to minus y over c sigma max divided by E. The moduli cancel out, and I get that the stress as a function of the y is minus y over c sigma max, also varies linearly over the cross section. And you can see that if you multiplied every point of this, profile view. So here, let me, bam, bam, bam. If I multiplied every point here, by the modulus, I would get that here, this would be a compressive or negative stress here, meaning going stress in this direction, causing compression. that is, again, I'm just multiplying all the strain values here by a constant, and that gives me this stress profile, meaning that I have sigma max here, sigma max in compression, and at some distance y, right here, y, I have sigma in compression right there. And here, just like as before, then I would say that this bottom half is experiencing a tension. If I multiply this by uh, uh, the modulus of every strain value here, every strain value that's making up this line, by the modulus of elasticity of this material, then I would have tension. Bam, pulling on this, and this is the stress profile that my cross section is experiencing. Stress profile. Okay, and you'll also find later, if I could calculate the force resultant here, this force resultant right here, I'll call that C, and then this force resultant here of the tensile stress, this T, and the distance, this arm right here, and if I take this arm right here, and if I take moments, let's say about this point, I'm going to find that the applied moment, this mz, whoa, here, this, let's put that back in. I think I used some sort of blue color. This applied moment mz by equilibrium, this mz is equal to t times the arm, or the distance between the resultants, or c times the arm. Okay, it's just this, basically it's the couple, right? The moment is defined by the, really what's more is that this stress profile, just to make sure that things are clear here, this is really a rectangular section that the stress profile is acting on here, okay, and here. And so really this stress profile is a stress volume. This is a volume right here. Bam, like this, okay, right here. And here, this neutral axis line, I will go like this right here. Whoa, blue. Right here, this neutral axis line. And I have, this right here. It's a volume, right? That should have been red. This is a volume. That is still not red. This is a volume right here acting on the surface. And in the bottom half, I have a tension. I have tension going like this and like that. Okay? And essentially, this is a stress volume, or a stress. Sometimes you'll see the term stress block, right? So here, let me make my neutral axis green so that there's no confusion anymore. Here, this, and the neutral axis is really a plane, my neutral axis plane, and a plane on my cross section here. And so this force resultant T is really a volume calculation, okay? So that if I wanted to do some equilibrium of this, right? If I want to look at equilibrium of this cross section, so let's say we want to look at equilib of the cross section, and in particular, I want to look at some of the forces in the horizontal, some of the forces equal to 0, and I would say that here, that means that the stress over, the integral form of this, I want to sum up the stress over the entire area here. I have pure bending. I have no axial force applied here, or no internal axial force resultant going on. So all of this should just equal to 0. And if I substitute the definition of stress here, it would be, it would be sigma max times over C times negative y dA equal to 0. And here, these are constants. These are constants. So I can take that out. This minus sigma max over C is y dA equal to 0. And the only way for that to be true is for this to equal 0. This must equal 0. And the only way that this thing equals 0 is if the neutral axis is at the centroid. Neutral axis is at centroid of the cross section. This is the first moment of area, okay? This is that first moment of area. And to be a little bit more precise, this is the geometric centroid of my cross section. The neutral axis is at the geometric centroid. Okay, so that tells us one thing. Now, if I take moments about the z-axis, so here, let's take moments. So we're going to take moments about the z-axis, which is, let's see, we have y, x. X was going this way, and z is going, bam, this way right here. So if I take moments about the z, and just as I said before, this moment, it really has to equal the applied moment. So if I take moments about the z, so here, let's apply that second equilibrium equation. Equilib, which is the sum of moments. Okay, so here I say the sum of moments about z has to equal the applied moment. Let's call this m applied. My bad, I shouldn't have done that earlier here. Hopefully it doesn't confuse you. Let's call this m applied right here, or m internal, whatever that internal moment is. Let's do internal. Okay, this internal moment m right here, this sum of the moments about z has to equal m, which means that here in integral form, this would be, we had sigma dA for the force. We would have y times sigma dA, okay, for the moment. And that means that m is equal to, and again, I substitute this whole business right here into here, right there. And that would say that I have minus y squared over c times sigma max dA, and you've all seen this before, and here I have this m is equal to minus sigma max over c y squared dA. This right here, this business right here is the popular second moment of area, which is also the area moment of inertia. And here, the definition of moment of inertia is resistance to bending, okay, or resistance to rotation of the cross section, okay, resistance to rotation, if you will, right here, or resistance to bending, in terms of my cross section, the geometry, how well can it resist rotation or bending? And the larger the I, this was the symbol I that we use right here, this I, the larger the resistance to bending, right? And so this moment is equal to minus sigma max over c times I. And so in this case, where sigma max is on the compression side, we would say sigma max is equal to mc over I. And usually when you're looking for the maximum value, you really just need an absolute value. Okay, we want to know the absolute maximum normal stress due to the moment right here. And in general, this is probably the more important equation. In general, right here, and let me do this in blue, sigma, the normal stress, is equal to minus my over I. Okay, and I call this the most selfish equation in the world because it's, my and I, and it's negative, right? And usually, depending on, what you believe, selfishness is negative unless you're a big Ayn Rand fan, right? In that case, it's good, all right? But anyways, whatever, right? I call this is our Flexure formula. This is the Flexure formula that's very important to know, okay? And that you should know for, as long as you're doing any sort of mechanics or stress analysis or anything, right? Anytime you're dealing with beams, you should know this Flexure formula. And this is the basis for which we design as well. And so here, one more thing here, this moment of inertia, is about the z-axis, okay? The z-axis meaning the horizontal, or this cross-section right here. So it's the moment of inertia about the z, okay? About the centroid of the cross-section right here. And this is my Flexure formula. And this is what we want to be able to use. This is one of our other fundamental equations that we want to be able to apply in an introductory course in mechanics. All right, hopefully you enjoyed, and we'll do some example problems next. Enjoy. Bye.